Welcome to this lecture. In this lecture, I am going to talk about Einstein's theory of specific heat. So, in the early lecture, I concluded that specific heat of solids solids cannot be explained at low temperature using classical theory, or in other words, I can say that Coulomb and Petit's law. That means this theory needs some modification. So, to account for low temperatures, specific heat solids, Einstein in 1907 he applied the quantum theory and he made certain assumptions. So let us talk about some assumptions which were made by Einstein to explain the specific heat of solids. So first assumption is that all the atoms are identical. All the atoms identical and independent simple harmonic oscillators. This is the first assumption. Second assumption is that all the atoms vibrate in identical environment and having same natural frequency and having same natural frequency third assumption is that energy spectrum of atomic oscillators energy spectrum of atomic oscillators is not continuous as this thing is assumed in the classical picture or the classical theory. And that means if it is not continuous, that means each oscillator has discrete value of energy that is En is equal to n plus 1 by 2 h cross omega, or you can write down it as h nu, not h cross, but it is simply h nu. It is the energy of the quantum harmonic oscillator as stated in case of quantum mechanics, and the value of n will be 1, 0, 1, 2 and 3 and so on, where h is the Planck's constant and its value will be 6.63 into 10 raised to the power minus 34 joules second. Then fourth assumption is that each atom behave as three independent harmonic oscillators. Oscillator means this is due to each atom has 3 degrees of freedom. Because of that, we are assuming that each atom is behaving as a 3 independent harmonic oscillator. This means that means if we are having a solid having n number of atoms, that means it contains 3n independent harmonic oscillator. And each oscillator having frequency nu. Then fifth assumption is that as each oscillator has distinct locations in the crystal, that means they are distinguishable so if they are distinguishable, that means they obey Maxwell-Boltzmann statistics. Right. So these are the 5 assumptions of Einstein's model for the specific heat. So if we keep all these assumptions in mind, then the energy of oscillator is given as that En is equal to n plus 1 by 2 h nu Or in some text, you can also write down it like this: h cross omega, where n is equal to 0, 1, 2, 3, and so on. If we will put n is equal to 0, then half h nu is the 0 point energy, and it is independent of temperature. And contribute for internal energy of oscillator. And contribute for means this term half h nu. This contribute for internal energy of oscillator. Also, we know that this oscillator follows Maxwell-Boltzmann statistics. So, average energy, this is the average energy, and it can be written as, using Maxwell-Boltzmann statistics, it is En e raised to power minus En upon kT whole divided by summation n is equal to 0 to infinity. It is e raised to power minus En upon kT. And let me put the values of En, because En is equal to n plus half h nu. So if I put all these values here, then it will become summation n varies from 0 to infinity. So it is n plus 1 by 2 h nu e raised to power minus n plus 1 by 2 h nu upon kT. And in the denominator, I have to write down, it is summation n varies from 0 to infinity. And here it is e raised to power minus n plus 1 by 2 h nu upon kT. And let us call this h nu upon kT as equal to x. So if I put it like this, then this above equation, it will become equal to, it is h nu, it can be taken outside because it is independent of n. So I can write down it as h nu outside the summation n varies from 0 to infinity. It is n plus 1 by 2 e raised to power n plus 1 by 2 x whole divided by n varies from 0 to infinity. It is e raised to power n plus 1 by 2 and x. And let me open this summation. If I open this summation, then how things can be written? It is equal to h nu. I put value first of all, n is equal to 0. So if I put it like this, then it can be written as 1 by 2 e raised to power x by 2. Then corresponding to n is equal to 1, it is equal to 3 by 2 e raised to power 3x upon 2 plus 5 upon 2 e raised to power 5x upon 2 plus and so on. And denominator can be written as e raised to power x upon 2 e raised to power 3x upon 2 plus e raised to power 5x upon 2 plus and so on. And now this can be written as, because if I take uh, or if I recall derivative, then keeping that in mind, this can be collectively written as d upon dx of natural log of ln x by 2 plus e raised to power 3x by 2, it is x, plus e raised to power 5x by 2, and so on. That means if I take derivative of this thing, then it can be written as 1 upon x means this, and derivative of this part, so that means this is equal to this one. It's a simple trick which I am using. You need not to worry about it. It's a very simple trick. You can appreciate if you start taking derivative of this part, you will immediately get this one, and you will apply chain rule correctly. Now let me do little more mathematics. So it is h nu ddx of, it is ln e raised to power x by 2 is common, is up to here, so 1 plus e raised to power x plus e raised to power 2x plus, and so on. So it can be written in this manner. Now ln of this means product of this. It means it's equal to h nu ddx of ln of e raised to power x by 2 plus ln of, means I open, because I will use the formula that ln of a into b ln a plus ln b means natural log of this. So if I use this formula, so this can be written as 1 plus e raised to power x plus e raised to power 2x, and so on. And this will cancel out with it. So it is equal to h nu d upon dx, and here it is x by 2 plus ln e raised to power x, sorry, not e raised to power x, plus 1 plus 1 plus e raised to power x e raised to power 2x, and so on. Right. So let us do little more mathematics or little trick here. As I know that 1 plus e raised to power x, e raised to power 2x plus, and so on, and let me call it as e raised to power x is equal to y. So that means 1 plus y square, and so on. And it's like a geometric series. So it's like a geometric series, and geometric series is nothing but a plus ax plus ax square, and so on. It is a over 1 minus x. So if I use this here, it can be written as 1 over 1 minus y, or it is 1 over 1 minus e raised to power x, or you simply write down it as like this. It's equal to 1 minus e raised to power x raised to power minus 1. So that means this, sorry, this part can be written in this way. So it's equal to h nu, and the derivative of this part is 1 by 2, and let me take the derivative of another part, and it is ddx of ln 1 minus e raised to power x raised to power minus 1 and it's equal to h nu 1 by 2 and this minus can be taken here, so it will be equal to minus ddx of ln 1 minus e raised to power x, and its derivative is equal to 1 by 2 minus its derivative log is 1 over x, so that means 1 over 1 minus e raised to power x, and again its derivative applying chain rule. So if I take its derivative, let us have a look at it. Yeah, so now it's equal to h nu 1 by 2, and it is minus minus will become plus because its derivative will be 0 and its derivative will be e raised to power x with negative sign, so that negative will make it positive, so it is plus e raised to power x over 1 minus e raised to power x. That's what we are getting here. And let us do little more mathematics. H nu 1 by 2 plus e raised to power x over e raised to power x over 1 minus e raised to power x over e raised to power x. And here this will cancel out with it, and it is 1 over e raised to power x is simply e raised to power minus x, and this will cancel out with it. So it is h nu 1 by 2 plus 1 over e raised to power minus x minus 1. Right, that's what I am getting here. So that means in place of x I have to write down h nu upon minus h nu upon kt, because I have considered that minus h nu upon kt is equal to x, as I did in the beginning. Let me go back. Okay, let me recall that thing. Yeah, oh sorry, it is minus h nu upon kt, right? Minus h nu upon kt, that's what we have to assume it as x, and keeping all these things in mind, I'm getting this. So it means this E average, which I am getting h nu 1 by 2 plus 1 over e raised to power minus x minus 1, whether it is minus or yeah, it's minus 1. So it is equal to h nu, it's 1 by 2 plus 1 over e raised to power h nu upon kt minus 1, and let me, it is 1 by 2 h nu plus h nu upon e raised to power h nu upon kt minus 1. Now let me write down the total energy, because it is the average energy. So now total energy is equal to that is U is equal to 3Ne, because there are 3N oscillators. So it is 3N h nu upon 2 plus 3N h nu upon e raised to power h nu upon kt minus 1. Now our purpose is to calculate the specific heat, and this specific heat is equal to du by dt at constant volume. So it is d by dt, it is the temperature, it is 3 by 2n h nu plus 3n h nu upon e raised to power h nu upon kt minus 1. So the derivative of this part will be 0 because this is constant. So it is equal to 0 plus d upon dt upon 3n h nu upon e raised to power h nu upon kt minus 1. That's what I want to do here. So it is 3n h nu. It's a constant. It can be taken outside. So now I want to take the derivative of this. So it is e raised to power h nu upon kt minus 1 and whole raised to power minus 1. That's what I want to calculate. And as I know that ddx of 1 over x is equal to minus 1 over x square. So if I use this identity then and apply the chain rule here, so it is minus 3n h nu e raised to power h nu upon kt minus 1 raised to power minus 2, and again the derivative of e raised to power h nu upon kt minus 1, and this will be equal to minus 3n h nu, and its derivative will be e raised to power and this this will go to the denominator, so it is upon e raised to power h nu upon kt minus 1 raised to power 2, and its derivative will be e raised to power h nu upon kt, and again derivative of h nu upon kt, right? So if I take its derivative, then it can be written as minus 3n h nu exponential of, or not exponential but e raised to power h nu upon kt and minus h nu upon kt square, its derivative, and whole divided by and e raised to power h nu upon kt minus 1 and whole square. And if I do little mathematics, then this part can be rearranged as that Cv is equal to 3nk exponential of h nu upon kt h nu upon kt square. I simply rearrange this part with it and multiplying and dividing by k, like that. It's a little mathematics. You can do it at your own. So it is exponential of h nu upon kt minus 1 whole square, right? So this is the equation for Cv which we are getting, and let us define a term. Let theta is equal to h nu upon k. This is known as Einstein temperature. Einstein temperature This is Einstein temperature. So if I use this small notation, then I can write down it as it is 3nk exponential of theta e over t, theta e over t square, and whole divided by exponential theta e by t minus 1 and whole square. And let me rewrite it as it's equal to 3nk theta e by t whole square and exponential of theta e by t whole divided by exponential theta e upon t minus 1 and whole square. And this nk is basically r, so I can write down it as 3r theta e by t whole square exponential theta e over t and exponential theta e over t minus 1 and whole square. So this is the expression for CB, and let us try to plot this equation. And if I plot this equation, the equation which we are getting is like this, and it's a very interesting equation which we got. The equation is that CV is equal to 3r theta e over t whole square exponential theta e by t whole divided by exponential theta e over t minus 1 and whole square. And let me plot it. So if I plot this equation, then I'm getting such type of equation, and this corresponds to 3r, and so this curve predicted from Einstein's equation which we got from here, and these are the certain points and these are the experimental points, right? These are the experimental points or the experimental values. So that means at lower temperatures, even Einstein's equation resembles with the experimental values. It's very much closer to that, but it is not exactly similar to the experimental values. There is a small mismatch at the lower temperature because it is CV axis and it is the temperature axis. So that means at lower temperature, Einstein's equation is not exactly resembling with the experimental value. So that means there are some drawbacks with it. Right. So that means specificity decreases more slowly than the predicted by this model. So this is the drawback of this model. So in the next lecture, I will talk about that how this drawback can be removed. Uh, but before moving towards that, let us try to find out the specific heat at higher temperature using Einstein's model. So now I'm going to talk about specific heat at higher temperature. Specific heat at the higher temperature. So as h nu is very much smaller than kT because temperature is very high. That means I can say that theta E is very much less than T, or we can say that T is very much greater than theta E. So that means e raised to power theta E by T, this T is very large, and if I expand it, then it can be written as theta E over T plus 1 by 2 factorial theta E by T whole square plus 1 by 3 factorial theta E by T whole cube, and so on. And these higher order terms can be neglected because this T is a very large quantity, right? So that means these terms can be neglected. So if these terms can be neglected, then Cv will become 3r theta E by T whole square and 1 plus theta E by T, because Einstein equation can be written in this way. So 1 plus theta E by T minus 1 and whole square, and this will cancel out with it, and this will cancel out with it. So both squares. So it means this 3r, this is a square, so that means this whole term will cancel out with it. So it is equal to 3r 1 plus theta E by T. So that means when T is very large, means T is approaching to infinity, then theta E by T, it approaches to 0. That means Cv approaches to 3r at high temperature. That means this Einstein's equation resembles with the Dulong and Petit's law at high temperature. That's what we have learned in the earlier lecture. Now let me talk about specific heat at low temperatures. Specific heat at the low temperature. So now T is very much less than theta E. So that means theta E by T is very much less than 1. Sorry, very much, not less than what, very much greater than 1. So Cb is equal to 3r theta E by T whole square exponential theta E by T whole upon exponential theta E by T minus 1 and whole square. So that means this theta E by T is very much greater than 1. In that case, this 1 can be neglected because this term is a very large term. So if 1 can be neglected, then I can write down it as 3r theta E by T whole square and exponential theta e by t whole square, sorry, not square, will not be there, and divided by exponential theta e by t whole square, and this will cancel out with it. So that means this Cv at low temperature, it is 3r theta e by t whole square exponential minus theta e by t, because it goes to there, right? So that means it is exponentially decaying. So it is the exponentially decreasing temperature. So that's what is happening at the lower temperature, right? That's what we predicted in the graph. So there is a little drawback in the Einstein's model, and the drawback is that in Einstein's model of lattice specific heat of solids, each atom is supposed to vibrate as a single unit independently. And this is the major shortcoming of this Einstein's model, because actually atoms are bound to each other. So that means they cannot be treated as isolated or independent oscillators, right? That means the system is behaving like a coupled oscillator. So later Debye uh, modified the Einstein's model, and he assumed that atoms are not independent oscillators, what they are like a coupled oscillator. So in the next lecture, I will talk about Debye model. So first of all, I will discuss the assumptions of the Debye model and try to calculate the specific heat of solids, right? So thanks for watching this lecture.